We've been working with exponential and logarithmic equations, and now it's time to see where those equations come into play. Previously, we looked at some instances where we talked about, growth and decay of a population, and those are generally going to follow exponential growth functions, or exponential growth or decay functions, exponential functions in general, given certain criteria. So we're kind of sweeping that stuff under the rug for right now. When we look at loudness, pH, magnitude of an earthquake, those are all log functions, and we can use logarithms to model the behavior between the quantities. Okay, but really what I want to focus on in this video is the exponential growth and decay model. Okay, now above I use A of t. That can represent amount. If we use P of t, tomato, it just depends on what we're talking about. In the context of a population, that's why we're using P. P of t represents, so P of t represents the population at time t. Could be in years, could be in seconds, could be minutes. Okay. P sub 0 represents the population, or the initial population. Let's write it as that, initial population. Now, R technically has a weird definition. You need a little bit of calculus to really understand what it is. But what we're going to think of it as is the rate constant. So it could be growth or decay, but it's saying, it grows by 5% each year or something like that. Okay? And then t is, of course, going to be time in years, or months, or seconds, or minutes. Okay? Some time unit. Okay? So now that we kind of know, and then similarly, if we change our notation to A, it would just be amount at time t, an initial amount. So an amount or population doesn't much matter what we're using this for. Okay. The other thing that we can also be aware of, we're not going to talk about it in this video extensively, but this equation P of t equals P naught e to the RT, I think of it as PERT. I don't know, like PERT Plus if you've ever used that shampoo. It's stuck in my brain forever now, but we can look at growth or decay of an investment, so like a car, a bank, a house, or bank account, a house. And we're just going to focus on mainly health science applications. So here's an example. So we're looking at Texas, and historical data shows that at the new millennium, Texas had approximately 21 million people in it. And then if we look 10 years later, so a decade later, the population was about 25.2 million. So we want to write an exponential model that represents the population of Texas t years after the year 2000, and figure out what k is. So k, you can use k. Some people use r. K or r, they are used interchangeably. So round r to 5 decimal places. Okay? Well, so the funny thing here is, I think if we look at P of t is equal to P naught e to RT, or KT, it doesn't matter. We actually know what P naught is. P naught would be the amount present at the beginning, and the initial. And so since our model begins at year 2000, and it's also defining t as years after 2000, that just means that P naught is 21. Okay. So, okay, this is good. Now, how do I find, and my function needs to have t left in it, right? So I need to figure out what r is. Well, how do I do that? That's where that other information comes into play. So I know that if I look at this data point, right, that's the same as saying P of 10 is 25.2. So then what I'm going to do is, instead of writing P of t, I'm going to say this is 25.2 is equal to 21 times e to the r times 10. And, okay, this is an exponential equation, right? I need to isolate the exponential. Okay, now I got my general process. isolate the exponential, so I have 25.2 over 21 is equal to e to the 10r. Okay, I'm going to apply a logarithm on both sides. That was step 2. Okay, I'm going to come up here. Apply a logarithm on both sides. Don't care which one it is. Oh, I basically maybe natural log would be useful. So I'm going to apply a natural log to both sides. And I'm going to get natural log of 25.2 over 21 is equal to natural log of e to the 10r. Well, okay, I know that natural log and e cancel, so this is just like saying the right side is 10r. Oh, and then just solve for r by dividing by 10. Natural log of 25.2 over 21 all over 10 is equal to r. Now, I know many of you are chomping at the bit like, oh my god, I need to calculate, I need to calculate, I need to calculate, and I get it. Now, this is technically the best answer you can give, but it does say round to 5 decimal places. So, okay, let's get out our calculator and do the calculation. And if you do, double check my number crunching, but I got 0.0182 3 if I'm following, let's see, so that's 2, 4, 5. 5 decimal places. Boom, there it is. Okay, so am I done? No, because it says write a function. Okay, follow the damn instructions. Okay, so P of t is equal to 21 e to the 0.01823 t. And then I'm done. I followed all the instructions. Yahoo! Okay. Part B, use the function to predict the population in 2020. Okay, so 2022 is 22 years after year 2000. So plug in 22, you number crunch, okay, and you get 31.4-ish million. Okay. So, okay, that's fine. Now part C, this is the whole reason we did this problem. We had to get to part C. So we're going to use the function to determine the year in which the population will reach 40 million. So, okay, so that's saying P of t, I don't know what t is, but I want it to be 40. So then, okay, well 40 can be equal to 21 e to the 0.01823 times t. And then, okay, solve this. So I want to solve for t, right? Solving the exponential. So divide and then log both sides. So I'm just going to skip a few steps. I'm going to get natural log of 40 over 21 is equal to 0.01823 times t, and dividing I get, and then calculating, I get t is approximately 35.3 years. Okay, so that's just a quicker example about how to use the exponential model. Okay, now another example of using this function. So the P of t is equal to P naught e to the RT, KT, whatever t, so you can use different things there, is where we have exponential decay. So we have, instead of things growing, it decays. So carbon-14 is used commonly to help do radiocarbon dating, and so they take the measurements of this particular isotope of carbon and look at the amount remaining after a certain time, and that helps determine the age of certain substances. So we know that the half-life of carbon-14 is that. Determine the age of a bone that has 42% remaining, round to the nearest 10 years. Oh man. So I don't know a lot of information here, but here's what I do know. When time is 5,730 years, P, the amount that I have, is half of the initial, right? Because that's what half-life means. It's the amount of time required for half to remain, or half to deplete, depending on your half glass full or half glass empty. Okay, so if we use that, let's see what that'll give us. So I have P of t is P naught over 2 is equal to P not e to the k times 5730. Oh, that allows me to get k. And so if I divide both sides by p sub 0, I would have 1/2 is equal to e to the 5730 times k. Natural log both sides and divide. Moral of the story is I get natural log of 1/2 over 5730 is my value of k. Now, yes, you can round if you need to. I'm not going to. But now what I really want to know, the question that is being asked of me is how old, so t I don't know, is a bone that has 42% of its original. So now the amount remaining is 42% of its original. So that's 0.42 times p0. And I need to figure out what t is now knowing what k is. So this information allows me to say that, okay, I have 0.42 p0 in place of p of t is equal to p sub 0 e to the k, which is natural log of 1/2 over 5730 times t. Okay, divided by p0 to both sides. Okay, that's fine. Natural log both sides. And natural log of 0.42 is equal to natural log of 1/2 over 5730. 5730 times t. Divide and solve. So t is going to be natural log of 0.42 over natural log of 1/2 divided by 5730. And if you do this out, I get 7,170 years, rounding the nearest 10 years. So approximately that old. And I would write a sentence to that effect. Okay, so just outlining what I did. Okay, I used half-life. Okay, so this half-life information allowed me to say, okay, at this time, half of the original remains, which led me to this equation and allowed me to figure out what k is. Then I used the second bit of information in the last sentence, or second to last sentence, to say, okay, I don't know the time, but I know that there's 42% of the original amount remaining. So then that allowed me to substitute, use the value of k to determine t as about 7,100 years. Okay, so this is a longer video. Thank you for staying with me. We are going to be using this exponential model all over the place. So let's get some practice in class.